We're going to talk about basic derivative properties and rules, and we're going to look at a whole bunch of examples. So let's first of all look at this example. If f of x is x squared minus 5x plus 3, find f prime of x. Okay, and then once we've done that, find f prime of 0 and interpret it in terms of the graph. Now, let me just say, once we know the rules for derivatives, once we know these little tricks, we'll be able to find the derivative just almost immediately. In fact, I can just look at this and say f prime of x is going to be 2x minus 5. Okay, once you know the rules, you'll just be able to know that just immediately. And so what this tells you is that f prime of 0 is, well, let's plug in 0 for x. It will be 2 times 0 minus 5, which is negative 5. So what that tells us is that the slope of the tangent line at 0 is negative 5. Now let's look at a graph in Desmos here. This is the graph of the function x squared minus 5x plus 3. And then the question was, at 0, what is the derivative? What's f prime of 0? And notice f of 0 was 3. Okay, f of 0 there is 3. But what is f prime of 0? What is the slope of the tangent line there? Well, it turns out it's negative 5. Okay, so that was real quick, right? Notice how easy, how simple that was. Well, if you do this the old way, right, the way that we did in the last video, it's kind of a pain. In fact, let me remind you of that way real quickly here. If we use the definition of derivative to find the derivative, rather than the quick rules here, this is how we did it. Remember, f prime of x was the limit as h approaches 0 of f of x plus h minus f of x all over h. And we had to do some scratch work to figure out what's f of x plus h, right? F of x is this. F of x plus h, the way you find that is to replace all the x's in the formula for f of x with x plus h. Okay, so we'd have x plus h squared minus 5 times x plus h plus 3. And then you'd have to FOIL out what's x plus h squared, right? X plus h times x plus h. If you work that out, you get this big long expression here. And we have the minus 5x and minus 5h right here. We get this big, huge expression for f of x plus h. And so we plug that in here. So that's what's in parentheses here. And I'm going to go through this quickly because we did this in the last video. So I don't want to go through all the details. It'll just take a long time, but I'm just reminding you, this would be f of x plus h, and then f of x was x squared minus 5x plus 3. And fortunately, you get some nice things to cancel out. You have the x squared cancels with a minus x squared. You have this minus 5x canceling with a minus 5x, which is a plus 5x. And you have this 3 canceling with a minus 3 there. So all three of these terms cancel with terms here. What you're left with is 3 terms on the top. All three of those terms have an h in them, so you can factor out the h like this, and then cancel the h. And then when you're taking the limit as h approaches 0, if you plug in 0 up here for h, you get 0 over 0. But now that you've canceled the h's, once you plug in 0 for h, you just end up with 2x minus 5. So notice you get 2x minus 5, which is what I said it was going to be right up here. And by the end of this video, you'll be able to know the derivative of this is 2x minus 5 just immediately. Just looking at it for a half a second, you'll be able to know the derivative is 2x minus 5. You won't have to go through this big long mess, right? So you found the derivative is 2x minus 5. So the derivative at 0, again, you just plug in 0, you get this. Now, again, I'm not going to work this example all the way out, but suppose you had f of x equals x cubed. How would you find f prime of x? Well, with the rules, you'll be able to know the derivative just immediately. And I'll explain these rules in just a second. The derivative is going to be 3x squared. Derivative of x cubed is 3x squared. Okay, now the rules will do that real quickly, but the long way of doing that is to do it like this. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And then you'd have to figure out what's f of x plus h. Well, f of x was x cubed. F of x plus h is x plus h cubed. And that's not just going to be x cubed plus h cubed. You have to FOIL out x plus h times x plus h times x plus h, right? Just like we did over here in the scratch work. And that's a big mess. You do x plus h times x plus h, FOIL that out, and then multiply that by x plus h. You get this big, long, messy expression, which you plug in here for the x plus h cubed. Fortunately, we have a x cubed minus x cubed. Those cancel out. You're left with 3 terms on the top, these 3 terms, and all of those terms have an h in them. So just like before, you factor out the h, and then you cancel the h, and you're left with this, and then you plug in 0 for h. When you plug in 0 for h, and again, we're plugging it in for h, not for x. When you plug in 0 for h, this is 0, this is 0, and you're just left with 3x squared. But again, you'll be able to know just immediately that the derivative of x cubed is 3x squared if you know the rules. Okay, so you can avoid all this painful work here, right? So I just wanted to show you all this work so you could see, man, that's a big pain. So it will be really nice once you know the rules. Okay, so if f of x is x cubed, f prime of x is 3x squared. If we wanted to find like what's f prime of 2, well, we just plug in 2 then for x and you get 12 as a result. So graphically what this means, here's the graph of f of x equals x cubed. At x equals 2, what is the slope of the tangent line, right? F of 2 is 8. Turns out f prime of 2 is 12. That's the slope of the tangent line there. Okay, so what are the rules? Or what are these tricks that we can do to make it quick to take a derivative? Well, the first theorem that we have is that the derivative of a constant function is equal to 0. In other words, if f of x is a constant, like if f of x equals 5, then the derivative is going to be 0. And this makes total sense because imagine, what does the derivative look like? Well, for a constant function, isn't the derivative, or isn't a constant function just a horizontal line? And at any point on the horizontal line, the slope's going to be 0. All right, so if f of x equals 5, right? So if this is up here at a height of 1, 2, 3, 4, 5, f of x equals 5, right? There's the function. What is the slope of the tangent line? Well, the slope of the tangent line at any point is going to be 0. So f prime of x will be 0. So the derivative of any constant function is just going to be the 0 function. Okay, now the next rule is going to be extremely useful. It's called the power rule because we're looking at powers of x, but actually it's a powerful rule because it allows us to take derivatives real easily and real quickly. Now, suppose we're trying to find the derivative of x to the n. What is the derivative of x to the n? Well, the power rule says the derivative is going to be n times x to the n minus 1. So for example, f of x equals x cubed, right, which we just looked at. What is f prime of x going to be according to this rule? Well, here the n is 3, so the derivative is going to be 3 times x to the 3 minus 1, right, which would be 2. It's 3x squared. Okay, the derivative of x cubed is 3x squared. Notice how quick that was. Notice how much simpler that was than trying to do limit as h approaches 0, blah, blah, blah. Okay, so let's do some more examples. Find f prime of x if f of x is x to the 7th power. Well, here n is 7. What is f prime of x? Well, the derivative of f of x, right, f prime of x is going to be 7x to the 6th. Right? 7x to the 7 minus 1, 7x to the 6th. Okay, what's the derivative of x to the 4th power? Well, according to the power rule, the derivative of x to the 4th is going to be 4x cubed. Okay, what's the derivative of x squared? Well, the derivative of x squared is going to be 2x to the 1, or in other words, just 2x. Okay, now you might wonder, why is the power rule true? Well, you can prove the power rule using something known as the binomial theorem, but one way that you might be able to guess the power rule is by trying to find the derivative using the old way, the hard way, with like x squared and x cubed and x to the 4th power, and you might notice a pattern. Okay, but you would prove this using the binomial theorem, but we're not going to go through the proof. But notice how much simpler it is now to take a derivative of x to some power. Okay, let's look at another theorem about sums and differences of a function. This says that the derivative of the sum of two functions is equal to the sum of their derivatives. The derivative of the sum is equal to the sum of the derivatives. And same thing, the derivative of the difference is the difference of the derivatives. But we do have to be careful. It's not true for products and quotients. The derivative of a product is not equal to the product of the derivatives, and the derivative of a quotient is not equal to the quotient of the derivatives. To do those, we're going to have to use something called a product rule and the quotient rule, and we'll talk about those in the next module. Okay, but it does work for sums and differences. So if we wanted to find the derivative of x to the 8th plus x cubed, right, if this is f of x, what is f prime of x? Well, f prime of x is going to be, well, the derivative of x to the 8th is 8x to the 7th. The derivative of x cubed is 3x squared. So there's our answer. 8x to the 7th plus 3x squared. Okay, what's the derivative of x to the 100th minus x to the 13th? Well, the derivative is going to be 100x to the 99th minus 13x to the 12th. Okay, we use the power rule to take the derivative of x to the 100th. It's 100x to the 99th. Use the power rule to take the derivative of this is 13x to the 12th, and we're taking a difference. Okay, the derivative of the difference is the difference of the derivative, so that's our answer. Again, notice how quick that was, how simple that was. Okay, the next theorem says, if g is a function and k is a constant, I don't know why I use g instead of f here, but if g is a function and k is a constant, then the derivative of k times g is equal to k times the derivative of g. Now, the notation here is a little messy and a little confusing, but the way I remember this is the derivative of a constant times a function is equal to the constant times the derivative of the function. And even saying it like that might be a little confusing, but let's do an example. Suppose we want to find the derivative of not x to the fourth, but 7x to the fourth. Okay, how would we find the derivative of 7x to the fourth? Well, f prime of x is going to be the derivative of a constant times a function. So the constant times x to the fourth will be the constant, 7, times the derivative of x to the fourth, which would be 4x cubed. Now, the way that simplifies is 28x cubed. Okay, so notice what essentially happened was you end up multiplying the 4 by the 7 to get 28. Okay, and then you lower that power by 1, you get 28x cubed. Okay, but we just did 7 times the derivative of x to the fourth, which would be 4x cubed. Okay, what about the next one? The derivative of 3x to the 10th. Well, this is going to be 3 times the derivative of x to the 10th, which is 10x to the 9th. And notice what you eventually get is 30x to the 9th. And you could have got the 30 just by multiplying the 10 by 3. And then you lower that power of 10 to become a 9. Okay, so usually I kind of skip this step right here and just go straight from here to here. Okay, in fact, let's do another example. What's the derivative of 5x cubed? Well, it's going to be 15x squared. 3 times 5 is 15. Lower that power by 1. Okay, 15x squared. And that's way simpler and way easier than trying to use f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h, and trying to do all that simplification. That takes a long time. These rules make taking the derivatives much simpler. Okay, what about the derivative of 10x to the fifth? Well, the derivative of 10x to the fifth is going to be 50x to the fourth. Okay, right, 5 times 10 is 50, and then lower the power you get, 50x to the fourth. Okay, and what about just 3x? Now, 3x is the same thing as 3x to the 1. So the derivative here would be 3 times x to the 0, but x to the 0 is just 1, so it's just 3. And actually, this makes a lot of sense. Imagine what does 3x look like? The function 3x looks like this, right? What is the slope at any point along the graph? Well, at any point, the slope is 3, so the derivative is just going to be 3. The derivative of 7x would be 7. The derivative of 5x would be 5. Or the derivative of negative 9x would be negative 9. Okay, so if you have a constant times x, the derivative is just going to be that constant. If it's just x, like x to the 1 power. Okay, now what about a polynomial? We should be able to take the derivative of any polynomial at this point. Okay, using the rules. So how do we take the derivative of x to the fifth plus 8x to the fourth plus 7x plus 5? Well, f prime of x, okay, the derivative is going to be 5x to the fourth plus, okay, we'll do the derivative of the sum as the sum of the derivatives. Here we have 4 things that we're summing up. We can still do derivative of the sum as the sum of the derivatives. Plus, it'd be 32x cubed, right? That's the derivative of this. Plus, what's the derivative of 7x? Well, that's 7. And what's the derivative of 5? Well, the derivative of a constant, remember, is just 0. So usually we don't even write that constant in the end. We don't write the 0 on the end. We usually just write it like this. Okay, the derivative is 5x to the fourth plus 32x squared plus 7. Okay, another polynomial. F of x equals 3x to the 7th minus 12x squared minus 13x plus 2. The derivative is going to be 21x squared, right? Again, you take the 7, multiply by 3, you get 21. Oh, not squared. Sorry, I goofed that up. X to the 6th. 21x to the 6th minus, what will it be? 24x to the 1. And I don't need to put the 1. It's just 24x minus 13, right? The derivative of 13x is just 13. And the derivative of 2 is just 0. We're not going to write that. So we get 21x to the 6th minus 24x minus 13. Okay, what about this one? What's the derivative of x squared plus 1? Well, this one's pretty straightforward. The derivative of x squared is 2x, or 2x to the 1. Derivative of 1 is 0. Notice it's 2x. Didn't we actually find this exact derivative in the last video? And wasn't it a long process of finding the derivative of x squared plus 1? Didn't we find that it was 2x, this exact one? And notice how quick it was. We could just write it down without even really having to think about it. Okay, so knowing these rules really helps making the process of taking derivatives go much easier. Now, let me mention a few things about notation for derivatives. If you're given a function f, or f of x, we could write the derivative as f prime of x. Now, another way to write the derivative would be df dx. Okay, so df dx, so df over dx, that means the same thing as f prime of x. Okay, these are the exact same thing. Okay, now what about f prime of a number, like f prime of 5? How could we write that here? Well, we'd write df dx evaluated at x equals 5. So we have this long kind of vertical bar right here, and we put x equals 5. Sometimes you just put 5 there, or x equals 5, however you want to write it. So df dx at 5, or at x equals 5. Now, sometimes we have functions where we're given them in terms of like y. Okay, so what would be the derivative of y? Well, you could write it as y prime, or y prime of x. You could write y as y of x, but this is y or y prime. Another way to write it would be dy dx. Okay, so y prime or dy dx, those both mean the same thing. Okay, so let's look at some examples here. If f of x is x to the 7th power, what is df dx? Well, df dx is going to be 7x to the 6th. Okay, df dx, remember that's the same thing as f prime of x. It's just another way of writing the derivative. Okay, if y equals this, x cubed minus 7x plus 15, what is dy dx? Okay, well, dy dx is going to be 3x squared minus 7. Derivative of x cubed is 3x squared. Derivative of 7x is just 7. And the derivative of 15 is 0. We don't even have to write it. Okay, now, sometimes you're given a different variable instead of f, or instead of x. What if you have f of t equals 2t to the 4th? 2t to the 4th, what is f prime of t? Okay, well, f prime of t is going to be 8t cubed. Okay, 8t cubed. Now, this could also be written as df dt. You wouldn't write df dx, you'd write df dt. But f prime of t, or df dt, is going to be 8t cubed. So we just have a different variable here. Or suppose we have g of w equals w squared plus 12w minus 8. What's g prime of w? Okay, well, g prime of w is going to be 2w plus 12. Derivative of w squared is 2w to the 1, right? There's 2w. Derivative of 12w is 12. The derivative of 8 is 0, so that goes away. And it's just 2w plus 12. Another way to write this would be dg dw. dg dw, or g prime of w, would be 2w plus 12. Okay, what about this? If f of x is 7x cubed, what is df dx at x equals 2? Now, again, this is just another way of writing what is f prime of 2. Okay, this notation here just means f prime of 2. So how do we find df dx at x equals 2? Well, first of all, what's df dx? Well, that would be 21x squared. df dx would be 21x squared. Now, what is df dx at x equals 2? Evaluated x equals 2, or applied at x equals 2. Well, we just plug in 2 now for x. So we'd have 21 times 2 squared. That'd be 21 times 4. 21 times 4, which would be 84. Okay, so remember, the derivative of a function, you end up getting a function, but the derivative of a function evaluated at a point. So if you're trying to find f prime of 2, or df dx at x equals 2, you end up getting a number. That number represents the slope of the tangent line at x equals 2. Okay, what about if we're given this in terms of y? If y equals negative 5x to the 4th, what's dy dx evaluated at x equals 1? Well, dy dx would be, first of all, without evaluating at x equals 1, dy dx would be negative 20x cubed. So what is dy dx evaluated at x equals 1? So this would be like y prime of 1. Well, we need to plug in 1 for x. We get negative 20 times 1 cubed. So that's just negative 20 times 1, which would just be negative 20. So the slope of the tangent line would be negative 20 at x equals 1. Okay, what about if g of t equals t cubed, what's g prime of 5? Well, g prime of t would be 3t squared. So what's g prime of 5? Well, g prime of 5 would be 3 times 5 squared, okay, which would be 3 times 25, which would be 75. Okay, so that's g prime of 5. Okay, I know I'm going through this kind of fast, but I'm just trying to get through the notation here, understand the notation. Now, one last thing with notation, which I haven't explained yet, is sometimes you'll see a derivative like this. This, if it says this d dx of this, okay, it's saying the derivative of this thing with respect to x here. What's the derivative of this with respect to x? By the way, these other derivatives, you might have a derivative with respect to t, for example, df dt, that would be a derivative with respect to t. But if your variable's x, we sometimes say the derivative with respect to x. This is just saying, what's the derivative of this? Well, the derivative of that is going to be 5x to the fourth plus 9. Okay, so d dx of this equals this. Or another way of writing the power rule, for example, would be, what would be d dx of x to the n? Well, it'd be n times x to the n minus 1, right? The derivative of x to the n is n times x to the n minus 1. Or what's the derivative of this thing with respect to t? What's the derivative of this? Well, the derivative is going to be 13t to the 12th plus 10t to the 4th. Okay, so sometimes you'll see derivatives written like this, or you could say, what's d dx of x to the 5th power? Okay, and I usually put parentheses. I know my math lab sometimes doesn't put parentheses around this, but I usually put parentheses around the x to the 5th. What's the derivative of x to the 5th? This is asking. Well, it's 5x to the 4th. So notice these rules make taking derivatives much simpler and much quicker. And they're really useful and really helpful compared to having to use the definition of derivative to find a derivative.